Okay, let us start. So here is the first slide. Can you see that? It says classical mechanics. And then subtitles, kinematics, dynamics, Newton laws, center of mass, pulley, circular motion, inclined plane, log stacking problem, oscillation, and waves. Can you see that? Can you see? Hello? Okay, so hopefully you can see that. So the second slide, we define classical mechanics as one of the oldest branches of physics and one of the most basic branches of physics. It describes motion of the bodies around us. Any questions? Maybe you can see better. Can you see better now? Hello? Are you with me?
Yes, sir.
Okay, welcome, welcome. Let me go back to the first slide. Can you see the first slide? It's called classical mechanics.
Yes, sir.
Did you have a chance to see this presentation? I've sent you the file earlier today. Hello? Please tell me if you can see that, if you can ask me some questions.
Yes, sir. I see the presentation.
Yeah, did you have a chance to see the presentation earlier today?
No, sir. I haven't chance.
Okay. Anybody has any questions before we start? No?
No, sir.
Okay. So then let's look at the second slide. Can you see the slides on your screen?
Yes, I see.
Nice. Okay. So the second slide discusses what classical mechanics is, and it is one of the oldest branches of physics. It is one of the most basic branches of physics. It describes motions of the objects around us, and mathematically, the equations of classical mechanics are very similar to the equations of quantum physics, of other branches of physics. So that's why it is so important to understand classical mechanics. Any questions about anything? Okay, then the next slide. The next slide discusses the limits of application of classical mechanics. We cannot describe very high speed in classical mechanics. We cannot describe very small distances in classical mechanics. So I would say that classical mechanics is usually used for objects from about 1 micrometer to several kilometers in size, and speeds from 0 meters per second to several kilometers per second. So beyond that, we usually don't use classical mechanics. Can you answer a question about use of classical mechanics? Where it can be used and where it cannot be used. Are you still with me?
Yes, sir.
Yes, sir.
Okay. Do you have any questions about the limits of use of classical mechanics or any other questions related to classical mechanics? Okay, let's look at material point then. The next slide, slide number 4. Material point is a model that we will use. Instead of considering large objects, we will consider just one infinitely small point in the center of mass of the body. And for many problems, it's good enough. For example, a bullet is very small compared to the building, for example, or compared to the earth or other objects which are much larger. Yeah. Even if the object is large enough, like a planet or star, sometimes we can reduce this enormously large object to its center of mass as a material point. And we will consider only infinitely small material point. Please ask me questions or please give me comments.
Sir, I want to
Yeah,
ask, at the
yeah,
and at the previous slide, it's white
yeah,
from
yeah,
0 to several speed of sound. Is that
yeah.
the limits? We know that there is a speed on like there is a like of speed. There is the limit of the classical mechanics.
Yeah, I agree with you that we must say the speed of light, but we cannot come close enough to speed of light. Because if you, for example, have speed of light, then it will be very different result. So it will be already relativity theory in play. So speed of sound is 1 million times smaller than the speed of light. And then several speeds of sound will be several millions of speed of light, which is not going to influence very much.
Oh,
Very good question.
okay. Thank you, sir.
Does it help?
Yeah, that's okay. I understand.
Yeah. Well, they say instead of saying several speeds of sound, they usually say much, much smaller than the speed of light. So in this case, several 100,000 times smaller than the speed of light. And also regarding the distance, I say several kilometers. It can be also a little bit different because even 1 kilogram of mass already causes gravitational pull. So and curvature of space and time. So again, this time general theory of relativity may kick in. So that's why I give like those vague limits. But on the other hand, they are more practical, because in the book they usually say much less than speed of light, and the distance is usually more than Planck's constant, which is like 10 to the power of negative 35 meters. But even at 1 micrometer, already quantum mechanics is significant. So we cannot really ignore quantum mechanics. But in the book, they say the distances are just much larger than 10 to the power of negative 35 meters. In this case, we have 10 to the power of negative 6, so that's like about 30 orders of magnitude difference. I hope it helps. Any other questions? Okay, if no questions, I would like us to move to slide number 5, momentum. And for a material point, momentum is the product of mass times velocity of material point. Okay, next slide. In this case, we see the equation number 1 shown for only one material point. P is momentum. It's equal to mass times velocity. Slide number 6, equation number 1. Equation number 2 shows the case of many material points, n material points. So we sum up. This symbol of sum means we're summing up m1 times v1 plus m2 times v2 plus m3 times v3, etc. Whatever the number of material points are in the system, we plus the momentums. Any questions? Hello?
I
11
think no, sir.
participants. Yeah?
I think
Question?
no. I think there's no question.
Okay, let's move on. Slide number 7. Collisions. Remember, last week we considered perfectly inelastic collisions, and we wrote equations number 3 and number 4. And number 4 is the solution, because only one velocity v in equation number 3 is unknown. So it is easy to express the unknown quantity of v using equation number 4, m1 v1 plus m2 v2, and the result must be divided by m1 plus m2. Here, m1 is the mass of the first body, m2 is the mass of the second body, v1 is initial velocity of the first body, and v2 is the initial velocity of the second body, and then they move together with velocity v. That's what we have done last week. I hope you remember. Yeah, but slide number 8 is something that we haven't done, and it's a bit more complex. So this time we have perfectly elastic collision. In other words, after the collision, we will have two unknown velocities after the collision, v1 and v2. So the first equation on this page, on this slide number 8, equation number 5, expresses the law of conservation of momentum, just like in the case of perfectly inelastic collision. But for perfectly inelastic collision, we had only one unknown value. This time we have two unknown values, so that we need the second equation. And the second equation is given by equation number 6, which expresses the law of conservation of kinetic energy. And v squared over 2 is kinetic energy. Any questions? Let's briefly look at slide number 9. It shows, I hope you can see, the picture. You can see how they collide, and you can see the solution of the equations for velocity number 1, v1, and for velocity number 2, v2. Any questions at this point? Okay, so slide number 10 says that momentum is conserved only in those two cases we considered before. In particular, absolutely inelastic collision, which we considered last week, and absolutely elastic collision, which we just considered today. Remember that we neglect any kind of resistance, including friction or air resistance. So it's perfectly without resistance. I mean, the collisions are without resistance. Any questions? Okay, then slide number 11 asks you to solve the elastic collision problem for these numbers based on your student number. And the code will solve everything. Just give the units and give the correct number of significant figures. Any questions about collisions or limits of classical mechanics? Hello?
So far, no questions, sir.
Okay. Okay. So let's move on to slide number 12. We continue with kinematics. The first equation on slide number 12 gives you the distance for constant acceleration a and initial velocity v naught and initial distance x naught at any time t. And the second equation gives you the expression of velocity of this material point at any time, v naught plus at, where v naught is initial velocity, a is acceleration, and t is time, anytime. So using the first two equations, using some algebra, we can find very useful equation number 3, which says v squared is equal to v naught squared plus 2a times, in brackets, the difference of distances x minus x naught. So the current distance minus the initial distance. And I'm asking you to prove that using just simple algebra. Any questions? Okay, so we are done with kinematics for now. Is that okay? Let's move to dynamics. Slide number 13. Dynamics studies motion of bodies under the influence of forces. Okay. Next slide, number 14, gives definition of mechanical system as the system which consists of many material points. Yeah. If we have like several material points, then the center of mass will be the weighted average. In case if we are dealing with continuous solid, then we need to use integrals. Yeah. Let's see how the center of mass is expressed on the next slide, number 14. It says center of mass. And we must remember that only external forces can change the location of the center of mass of a mechanical system. And here is the expression for 2 points. Can you see Cm is equal to m1 x1 plus m2 x2 divided by m1 plus m2? For 2 material points, this is the expression of center of mass. If the points are located along x-axis. If we have more points, then it will be plus m3 x3. If 4, then plus m4 x4, etc., and divided by m1 plus m2 plus m3 plus m4, etc., if you have more points. Yeah. Remember that the center of mass is different from the center of gravity. If you don't remember, then please be aware of that if you don't know that. Because we'll be dealing with center of gravity maybe either today or later. So I'm asking you to find the center of mass of 2 equal masses k meters apart, which is approximately like 7,000 meters apart. And I hope you understand that if the masses are the same, the masses will cancel out, and the center of mass for 2 masses will be in the middle between the 2 masses. And the code solves that. Any questions? No questions.
Sir, I want to ask some question.
Yes. Yes.
So this center of mass, we just find the center of the mass or anywhere or else.
If you are given several material points with the mass located along one axis, this is going to be the equation of how you find the center of mass. If, for example, you have 2 points, you have m1 and m2. m1 times x1, x1 is location of m1. For example, you have the masses on the straight line, right? So the first mass is, let's say, 1 kilogram, and the first distance is 1 meter, for example. And then the second mass is 2 kilograms, and the distance is 2 meters, right? So you do 1 times 1, which is 1, plus 2 times 2, which is 4, so that's 5, divided by 1 plus 2, 3. So 5 divided by 3. This is going to be the location of your center of mass. Does it help?
Oh, thank you for the answer, sir.
Okay, I hope it helps. The next slide talks about internal forces and external forces. So if you have a mechanical system, between the points of the mechanical system, there are internal forces. They cannot change the location of the center of mass. Only external forces can change the location of the center of mass. For example, the friction force, the gravity force, those external forces, right? So can I pull myself out of mud, and why? That's the question. The answer is, of course, I cannot pull myself out of mud, because my force is internal force, right? I'm the system, I am the mechanical system, which cannot change its center of mass. I will need someone's help to get out of mud. Yeah? I hope it's clear. Okay, the next slide, number 17, talks about kinetic energy. We've been dealing with kinetic energy already, and kinetic energy of a material point is mv squared over 2, where m is the mass of the material point and v is the velocity of material point. Yeah. So please note that if you take derivative from kinetic energy with respect to velocity, you will get mv, you will get momentum. Right? I hope you know how to take the derivative. Derivative of 2v is going to be equal to 2, right? But derivative of v squared is going to be equal to 2v, right? And if you take the derivative of kinetic energy, v squared becomes 2v. 2v divided by 2 is just v times m gives you mv, which is momentum. And it's really, really important property of kinetic energy. It's used everywhere in physics, in particular in quantum physics. So it's a very important property of kinetic energy. Questions? Okay, next, slide number 18. Potential energy is mgh in our case so far. mgh is potential energy. Here, m is the mass of material point, g is the gravity acceleration, and it's approximately 10 meters per second squared on Earth. And h is the height above some level, let's say above the ground. So the higher you raise the mass above the ground, the greater is potential energy. Questions?
No, sir.
Okay, the next, yeah, question?
No, there is no question in this
Okay.
slide.
Thank you, sir. Okay, so this is laws, these are laws of Newton, slide number 19. Probably the most important topic of classical mechanics. We have 3 laws of Newton. The first law says if there is no force, there will be no acceleration. So if there is no force, the body will move with the same velocity. It may sound a little bit strange because many people would say in order for something to move with the same velocity, it must be pushed by the force. But if you look at the second law of Newton, which says F is equal to m times a, force is equal to mass times acceleration, you can easily see that if the force is 0, then acceleration is also going to be 0 because mass is not 0. Yeah. So therefore, the first law of Newton can be derived from the second law of Newton if force is equal to 0. Yeah. We'll be using the second law of Newton almost everywhere for projectile motion, for pulleys problem, for many other problems like inclined plane and many other problems. We will have to solve the equations of the second law of Newton. And please note that acceleration is derivative of velocity, and the distance is derivative, velocity is derivative of distance, right? So that acceleration is the second derivative of distance. And we need not only acceleration, we need velocity, and we need the distance. That's what we will be looking for. To describe the motion of mechanical system, we need to know the distance at any time, and we need to know the velocity at any time. That's what we will be doing. And finally, the third law of Newton says that action is equal to reaction. I'm sitting on the chair. I'm pressing on the chair, but the chair presses back on me. So we are in mechanical equilibrium. I'm not moving because the chair pushes back. If there was no chair, I would fall down. But because there is a chair, I'm sitting on the chair, I'm not falling down. So that's the main idea of the third law of Newton. Questions?
Sir, I want to ask something.
Yes. Yes.
Are laws of Newton in this material very influential and must be memorized in classical mechanics?
I think it's better not to memorize anything at all. I think it's better to understand and to use it, and you will remember. I hope you will not memorize anything. I'm trying to give you all the equations, but I hope you will understand, and I hope you will use this in your everyday life so that it will be easy to know it. Okay?
Okay, sir. Thank you.
Thank you. The next slide is talking about mass. Yeah. Oh, there is a mistake here. It must be the measure of inertia, not inertial. The measure of inertia of body. It's the measure of how much body resists acceleration. Yeah, if something is really, really massive, for example, maybe a car, it's really hard to push a car so that it gets acceleration. But if you have, let's say, tennis ball, it's really easy to push it and it gets acceleration because the mass of tennis ball maybe, I don't know, maybe 100 grams or less, maybe 50 grams, whereas the mass of the car may be 1 ton. So that's the difference, right? So that's inertial mass. Yeah, but there is also gravitational mass. Okay, inertial mass has to do with the center of mass, but gravitational mass has to do with the center of gravity. So the Earth pulls all objects with the acceleration of approximately 10 meters per second squared. So that's the manifestation of gravitational mass. Yeah, so there are at least two interpretations of mass. Inertial from the second law of Newton and gravitational from gravity law of Newton. We will talk about that a little bit later. There is also a third type of mass, which is quantum mass. Maybe we can discuss that later, but just be aware of the different meanings of mass, and that's what I want you to tell me in your own words. Questions? Okay. If there are no questions, I would like us to get to slide number 21 and continue projectile. Remember, we started projectile last week, and we found the distance at any time. So as you can see, projectile is a particular case of motion with constant acceleration a, which is negative g, negative 10 meters per second squared approximately. Yeah. Projectile is described by the second law of Newton in 2 dimensions. So we have x direction and we have y direction. And as you can see, fx is equal to 0. So we have the first law of Newton along x-axis. So there will be no acceleration along x. But along y, as you can see, Fy is equal to negative mg. And that is equal to m times a. So there is a constant acceleration along y-axis. Okay? And to get velocity, we must integrate this equation of the second law of Newton. Yeah? Next slide, 22. So there's the expression of velocity after we integrate. Vx is equal to V naught cosine A, where A is angle of release, and Vy is equal to V naught sine A minus gt. Here t is time, g is gravity acceleration, A is the angle of release, and V naught is initial velocity. We use the initial conditions for velocity, that velocity at 0 is equal to V naught. Yeah. Here you can see the expression Vx of 0 is equal to V naught cosine A, and Vy of 0 is equal to V naught sine A. I hope you remember the picture from last week, where I draw the parabolic trajectory of the projectile, and you can see V naught angle of release and other things. Yeah. So I would like you to calculate velocity for your projectile. Okay. The next slide. I want you to calculate time of the motion of projectile. And we can find the total time by remembering that at the top, the velocity Vy is equal to 0. So therefore, let's look at slide number 22, okay? If Vy is equal to 0, it means that V naught sine A is equal to gt, right? Because we know Vy is 0, right? The second equation on slide 22. So that will give us the time of the maximum height, right? Because V naught is 0 at the maximum height, right? And the total time will be twice as big because maximum height is in the middle, okay? So that's why slide 23 tells you that total time is 2V naught times sine A and the whole thing divided by G. And the time for maximum height is half of that, which is V naught sine A divided by G. Here V naught is initial velocity, A is angle of release, and G is gravity acceleration. So slide 24 asks you, no, it's continued, right? Slide 24, sorry, repeats what we have done last week for the distance. Okay, so for projectile at any time, x distance at any time is equal to x naught, initial distance, plus time, times V naught, initial velocity, times cosine A. And y of projectile at any time is equal to y naught, initial y, plus time t times V naught, times sine A, where A is the angle of release, minus half g t squared. Here g is the gravity acceleration and t is time. Yeah, we also use the initial conditions, which means at time 0, x of 0 is equal to x naught, and y of time 0 is equal to y naught. That's how we get the equations for x and y. That's what we have done last week. Okay, you can also find y is the function of x. Slide 25. Maybe later, if we have time, I will show you how it works, because the drawing I drew last week, sorry, was x versus y. So it was parabola, and as you can see, it's also parabolic equation. Tangent tan A is tangent of angle of release, and tan A is equal to sine A over cosine A. Okay. You can also find initial velocity and corresponding angle of release to hit any angle, any point in space. So slide 26. So for example, if you want to hit any point with the bullet anywhere, you can always calculate minimum initial speed, minimum initial velocity of your bullet. And maybe later we can do it. Maybe I can show you how to do that. Okay, so slides number 27 and 28 ask you to find velocity. Slide 27, I ask you to find velocity for your projectile, for your student number. And slide number 28 asks you to find time. for your projectile and for your student number. And I give you the code, just consider using the code and then make sure you give the correct units and the correct number of significant figures. Questions, please. Any questions? Okay, slide number 21 discusses truck and trolley, and that's what we discussed last week. I showed you that, not that I showed you, sorry, I just told you. I told you that if you rotate the wheel, it is more effective and more efficient than if you pull the wheel or if you push the wheel. Yeah, that's what I would like you to discuss and to tell me about that, how you understand that. And the next slide, number 30, about collided eggs. Why the egg which is moving is more likely to crack than the egg which is not moving. This problem has also very deep philosophical meaning, far beyond physics, going to military science, going to self-defense, to many things. It's much easier to defend yourself than to attack someone. So, any questions before we go to pulley problem? Okay, so the pulley problem, slide 31. So you see there is a pulley, yellow pulley, and two masses attached to yellow pulley. Mass which is blue and mass which is red. So the blue mass in this case is 8 kilograms and the red mass is 5 kilograms. And the question is, what is the acceleration? Okay, let's look at slide 32, which gives you the explanation. I hope you can see that. You can see that we use the second law of Newton, that we project all the forces on the rope, which has the tension of T. Yeah. Then we solve for the acceleration and for the tension in the rope. Yeah. So in this case, the acceleration will be left down, the mass M capital on slide 32 is the same as the blue mass on slide 31, right? Because it has greater mass, it will pull down the smaller mass, and there will be corresponding acceleration. Okay, slide 32 shows you not only how we can find acceleration, but also how to find tension in the rope. Okay, remember we consider the rope to be massless and no friction. Questions? You must have many questions about this, because I don't explain in all the details how we find these things. But if you look a bit down, slide 38, it gives you the link to YouTube video, which also explains this problem. Okay, so in case if you still don't understand, maybe the YouTube video will help a little bit. So the blue mass will go down and the red mass will go up. Slide 31. They will have acceleration, which is expressed on slide 35. G is the gravity acceleration, M capital is the big mass, and M lowercase is the small mass. Yeah. So we write the second law of Newton on the direction of the motion. The first force is M capital G, in positive direction. The second force is negative m lowercase g into negative direction because it's smaller mass. It will be pulled by the bigger mass. And then the result is the sum of masses times the resulting acceleration. One equation, one unknown. Okay, and slide 36 tells you how to find the tension in the row using similar interpretation of second law of Newton. We consider the big mass, the force on the big mass from its gravity force is m capital G minus tension T and is equal to total mass, in this case m capital A. And we find tension, same thing for the smaller mass. These T's, T which is equal to m capital G minus A and T which is equal to m lowercase g plus A, they are the same. You can easily check that they are the same, okay? So let's go back to slide number 33, right? It tells you that this pulley problem is solved by projecting all forces to the chord. So it's one-dimensional motion. It's kind of more similar than projectile. Projectile is two-dimensional motion, and in this case, we have only one-dimensional motion, right? So if there are two non-zero different masses, acceleration is not g and not negative g. In other words, it's not doing free fall. Then there will be acceleration of the masses and tension in the cord. Cord means rope. When I say cord, it's the same as a rope. Yeah. We neglect resistance, slide number 33. We assume cord, which is rope. We assume cord to be massless. Tension is an internal force. We must remember that. But difference in weights will be external force, which will move the center of mass of the system. Okay? Any questions? So slide 34 tells you that if the masses are the same, then there will be no acceleration, but there will be tension in the cord or rope. If both masses are zero, then there will be no acceleration and no tension. I hope you can understand that, yeah? If one mass is zero, then there will be acceleration, but no tension, because there is no resistance in terms of the different forces pulling different directions, yeah? And finally, if acceleration is g or negative g, then there will be no tension, it will be free fall. Questions? Okay, so slide 37 asks you to find the acceleration of a simple pulley situation and the tension in the rope for two masses. Questions? I'm sure you have many questions. Please ask. Hello? Can you hear me?
Sir,
Yes,
I
yes.
want to ask something.
Yes.
Is the mass
Yes.
of the rope is calculated on this case?
No, it is considered to be massless. I think I have mentioned this in one of the slides. We neglect the resistance. We assume cord to be massless. Can you see slide number 33? It says we neglect the resistance. We assume cord to be massless. And of course, it is weightless because it's massless. It means it's weightless because weight will be m times g. M is equal to 0 for the cord or rope. Therefore, there is no mass. Any other questions? Rope has no mass. Cord has no mass. It's the same, cord or rope. Any other questions? Okay, so the next topic will be friction. Remember, before we also always said no friction, no resistance. This time we'll look at friction force. Okay, so friction is usually the resistance when the bodies slide against each other. So we often consider sliding friction, for which friction force F is equal to some friction coefficient mu times N, which is normal reaction. Usually it is equal to the weight of the body according to the third law of Newton. Yeah. So I will ask you to calculate the friction force if you are given the friction coefficient mu through your student number and the normal reaction N through your student number. I give you the code for that. I hope that should be quite easy. We will probably get back to friction a little bit later. Any questions about friction? Okay, so the next few slides are dealing with this formula, mv is equal to ft, which is very useful for many problem-solving cases. mv is equal to ft. Here, m is the mass, v is the velocity, f is the force, t is time. Okay, so this formula mv is equal to ft is simplified mechanical equation which says that change in momentum is equal to impulse of force. mv is momentum and f times t is impulse of force. So this equation, meaning mv is equal to ft, is a particular case of the equation of the second law of Newton. dmv over dt is equal to force. In other words, derivative of momentum is equal to force. And we can rewrite this as differential d of mv is equal to f dt. And then mv is equal to integral of dt. Yeah. So all that is basically the second law of Newton. So the next slide, I ask you to solve this problem for a dust particle with a given mass and speed and subjected to a force of given number of Newton. Yeah, so using this formula, mv is equal to ft, you can find t, which is mv over f. You know m, you know v, you know f. Please give the correct units and correct number of significant figures. And the next problem is about the biker, which starts from rest, and the friction coefficient is known. So you have friction force, right? Because normal reaction will be mg will be equal to weight. You have mass, so you have weight. You have t kilograms, for example, I don't know, 16 kilograms or whatever, or let's say 90 kilograms or whatever it can be, the biker's mass, right? Times g, that's weight, is the same as normal reaction. And you have mu coefficient, mu times normal reaction is your friction force, right? Then the velocity is unknown, but you know time, right? So you know force and time, and mass is also known. So you find velocity from this formula, yeah? Any questions? Okay, we go to rotational motion, slide, what is it, 43, right? So if we look at slide 44, it shows that something is moving around the circumference, around the circle, right? There is a velocity, there is acceleration, and we'll talk about this a little bit later. But let's go back to slide number 43, right? So we consider rotational motion. It is possible to consider rotation of a material point around the center of rotation, or rotation of a solid around the axis of rotation. The example of material point rotation around the center of rotation will be rotation of a satellite around the planet. Yeah, both planet and satellite are considered to be material points. Yeah. So in this case, as usually probably the period is equal to 1 over frequency, and frequency is how many times you rotate in 1 second. So the acceleration of rotational motion with the same angular velocity is given by v squared over the radius. V is the linear velocity, r is the radius, and omega is angular velocity, which is angle divided by time. Yeah. And the linear velocity is going to be equal to radius times omega, where omega is angular velocity. Okay? So slide number 44 shows you the picture of what happens. Just imagine, let's say I rotate a mass on a rope, and it goes with the same velocity, but because velocity changes direction, there is acceleration a, which is equal to velocity squared divided by the radius. Okay? Questions? Okay, the next slide asks you to find the linear acceleration due to the rotation for a person on a planet with a period of rotation 24 hours, just like Earth, and radius s millimeters. S is your student number, I think about 22 million, right? 22 million millimeters. So the code gives you the solution. Please note that here the acceleration is going to be in meters per minute squared, not per second squared. So please check this in the code. I hope you will see that. Okay, questions? Okay, now let's see what happens if the rope breaks during the rotation. What do you think will happen if I rotate something? If I rotate something and suddenly the rope breaks, where will the mass fly? What do you think? So will it fly away from rotation along the rope, but away, or will it fly following the tangent line, or maybe there will be something else happening? So according to the first law of Newton, if the rope breaks, there is no force acting on the mass anymore. So the first law of Newton kicks in, which says the velocity will stay the same. If there is no force, velocity will stay the same. So therefore, the mass will fly along the tangent line, not away from the center of rotation, but parallel, not parallel, but following the tangent line to the circumference, the tangent line to the circle. I hope you can understand that. Any questions? Okay, the next slide talks about comparison of rotation and translation. Translation means motion along the straight line. And let's compare it to rotation, okay? So slide 47 says that angle A for rotation and distance d for translation, angular velocity omega for rotation, and linear velocity v for translation, moment of inertia J for rotation. I will explain that to you a little bit later, hopefully. Moment of inertia is distribution of mass in terms of rotational resistance to rotation. Remember, mass is the measure of inertia for translation, but for rotation, it's moment of inertia. It's kind of distributed mass. Yeah, so therefore, moment of inertia for rotation and mass for translation, angular momentum J omega for rotation, and linear momentum mv for translation, kinetic energy for rotation, half J omega squared, kinetic energy for translation, half mv squared. Next slide, we continue. Torque, which means the rotational effect of the force. Torque for rotation, force for translation. You will hopefully understand that translation is rotation with infinitely far center of rotation. Okay? And when you consider the vectors of angular velocity, angular acceleration, torque, then you must be aware that they are perpendicular to the plane of rotation. Hopefully we'll deal with that a little bit later. And I ask you the question, and I hope you can compare translation and rotation. Questions? Please. Okay, next slide, 49. Energy, work, and power. Energy is the ability to do work. I hope you understand that. Okay. Remember, maybe in the secondary school, you were told that work is distance times force, the second line of this slide, right? W is work, D is distance, F is force. It is sometimes true, but not always. You see, I should write here dot product. I should make the vectors bold. There must be vectors bold. The fact is, it is better to say that work W is equal to vector D dot product vector F. Dot product, that means that we multiply D times F times cosine of angle between them. Okay? But even for more general case, you have work as curvilinear integral. Work W is equal to integral force F dd and integral F dd. F is force and D is distance, capital D is distance. Yeah. Hopefully we will discuss this in details later. And power can be work divided by time. That's what we were taught in high school, but more precisely and more accurately, power P is equal to derivative of work with respect to time, dW over dt. Okay, next slide. Power sometimes can be expressed as force times velocity. It is possible to show that that's the case. So P is equal to F times V. P is power, F is force, V is velocity. So I will ask you to explain the basics of energy, work, and power. Any questions? Okay, the next slide about conservation laws. We have conservation of energy and conservation of momentum. Yeah. Energy is conserved when force is derivative of some function. Remember, mgh is potential energy. And if you take derivative of mgh with respect to h, you will get mg, slide number 51, right? F is equal to d mgh over dh, and that's just mg. In this case, the energy will be conserved and momentum will be conserved. Yeah. I'm sorry. Momentum will not be conserved, but energy will be conserved in this case. Yeah. Momentum is conserved when there are no external forces. But in our case, there is external force. So momentum will not be conserved. It will be conserved if there are no external forces. So the conservation laws are the result of symmetry of space and time. Maybe we can discuss this later if we have time to discuss that. It has very deep philosophical meaning. So our space is symmetrical, our time is symmetrical in the case of conservation laws. And I ask you to explain conservation laws in your own words. Any questions? Okay, the next slide. Remember, I promised you to tell you about Newton's law of gravity. It is similar to the law of Coulomb. I'm sorry, I think I misspelled Coulomb. There you go. So there's the spelling of Coulomb. In electromagnetism, it is similar. So force F, slide 52, is equal to G constant times first mass times second mass, and divided by the distance between the masses squared. G is the gravity constant, which is approximately 6 times 10 to the power of negative 11. M1 and M2 are masses of bodies between which the force is. Yeah. And R is the distance between the centers of masses of the bodies. Okay. The next slide asks you to compare the gravity force on the equator, where we are now, we are close to the equator, and on the pole of the Earth. And pole is 21 kilometers closer to the center of the Earth than the equator. So therefore, on the pole, the weight will be greater than on the equator. And the code solves that and gives you the answers. Questions? Okay, the next slide then. Okay, so now we talk about escape velocity, orbital velocity, and gravity acceleration. If you want to fly to other planets, then you have to have escape velocity, which for the Earth is 11 kilometers per second. Can you see slide 54? V escape is equal to square root of 2gr. For example, for Earth, g is approximately 10 meters per second squared, and radius of the Earth is approximately 6,000 kilometers. And we find this equation for the escape velocity from conservation of energy. mgh is equal to half mv squared. So potential energy is equal to kinetic energy. It means that the escape velocity will be the same as if we drop this object, let's say satellite, from very, very, very far, let's say from millions and billions of kilometers to the Earth, provided there is only gravitational pull of the Earth and nothing else. So that potential energy of falling object will be equal to the kinetic energy on the surface of the planet. So mgh is equal to mv squared divided by 2. And we have m, we have g, we have h. We don't really need m because m cancels out, right? mgh and half mv squared. M cancels out, so it becomes gh is equal to half mv squared. Therefore, v is equal to square root of 2g h is r, h becomes r, radius. Yeah. Questions? Okay. If you don't want to fly to other planets, if you just want to be a satellite of Earth, for example, then you need to have orbital velocity. And orbital velocity is found from the equation of angular acceleration. Remember, v squared over r equal to the gravity acceleration g. So g is equal to v squared over r. And here v is the orbital velocity. So from this equation, orbital velocity is equal to square root of g times r. Okay? And finally, the gravity acceleration on any planet is going to be the force on this planet acting on 1 kilogram, right? So as you can see, the law of Newton of gravity has g m times m2 divided by r squared, but m2 is 1 kilogram. So just g, which is 6 times 10 to the power of minus 11. M is the mass of the planet, for example, Earth. And r is the radius of the planet, for example, the radius of Earth. So next slide, which is number 55, shows you, how things orbit around the Earth and how you can fly away from Earth if you want to fly to other planets. And then it shows the equator and it shows the pole and it gives you all the equations. Slide 55. Any questions at this point? Yeah. Say it again, please. I don't understand. Could you please repeat again? Yeah. Can be the same for the moon. Just plug the radius of the moon and mass of the moon. Mass of the moon is approximately 6 times smaller than the Earth's, and radius is also about 6 times smaller than the Earth. So the gravity acceleration on the moon is approximately 6 times smaller than on the Earth. So on the moon, it's about, I think, 1.5 meters per second squared or something like that. About 1.5. And on the Earth, it's about 10. I hope it answers your question. Okay. Okay, slide number 55 gives you the picture and the equations. And slide number 56, we use the law of gravity of Newton. Yeah. So I showed it to you before. So it's here again. F is the gravitational force of Newton. G is the gravitational constant, which is 6 times 10 to the power of negative 11. And then adjust the units. M1 and M2 are masses of the bodies. And R is the distance between the centers of masses of the bodies. Okay, slide 57 asks you to find gravity acceleration, orbital velocity, and escape velocity for a planet with mass S billion tons and radius S millimeters. Here S is your student number, which is approximately 22 million, right? Any questions? Okay, the next slide, 58, talks about the work energy theorem, which is probably the most important theorem in classical mechanics because you can solve almost any problem in classical mechanics using work energy theorem, which says that change in kinetic energy of mechanical system is equal to work of all external forces and all internal forces of mechanical system. Okay? You can illustrate use of this theorem using this equation for v velocity squared at any time is equal to v naught squared plus 2a times x minus x naught for constant acceleration. If you write a as force F divided by mass m, and then force times the distance will be your work, and m times velocity will be kinetic energy. Okay? Change in kinetic energy will be equal to work. Okay? Questions? Okay, now let's move to solid mechanics. We have solids this time, slide number 59. It considers rigid bodies. They cannot be deformed. For example, in fraction mechanics, in elasticity, plasticity theories, you can see the bodies which can be deformed can change their form, but not this time. Yeah, for rigid body, we can calculate m, which is torque or moment of force, as distance cross product force, and cross product means that you multiply distance times force times sine of angle between them. Remember, for work it was cosine, but this time it's sine. Yeah. In the secondary school, we were told that moment of force or torque is equal to force times distance. But that would be too simplified, too simplistic. In this case, the angle is 90 degrees, so sine of 90 degrees is 1. So that's what we have learned from the secondary school. But here we learn that moment of force or torque m is equal to distance cross product force. Okay. Next slide, number 60. Yeah. It's not possible to apply torque to a material point because material point is infinitely small. The distance is 0. There is no way to apply torque because the distance is 0, right? Remember, distance times force, distance is 0, therefore torque is 0 or moment of force is 0. Yeah, but solid has moments of inertia with respect to different axes of rotation. For example, you can have like car, for example, if you rotate car around its like axis, one axis, it will be one moment of inertia. If you rotate it around another axis, it will be another moment of inertia. And as I said, we will try to talk about moments of inertia a little bit later, probably not today, in details. Just remember that moment of inertia for rotation is equivalent of mass for translation. And as you can see, the second law of Newton for rotation is moment m or torque is equal to j moment of inertia times epsilon. Epsilon is angular acceleration. And I think I should make it bold here. It's a vector, angular acceleration. It says how quickly you accelerate motion, for example, around the circumference. Before we talked about constant velocity, but this time velocity can increase, so there can be angular acceleration of a solid, even of material point as well. It is possible to have angular acceleration for material point. Okay, questions? I'm sure you have a lot of questions because I couldn't explain many things deeply enough and in enough details. Okay, let's try slide number 61. Okay. We should be aware that the force vector is the sliding vector. You cannot move the force away from its direction. It can only slide along the direction. Because if you move the force away from its direction, even if you make it parallel force, then it will cause additional moment or additional torque. Yeah. So force is not a free vector. Force is a sliding vector. whereas vectors of torque, velocity, angular velocity, momentum, angular momentum can be applied at any point. So they are free vectors: torque, velocity, angular velocity, momentum, and angular momentum. They are free vectors. You can apply them to any point of the body. You can translate them as long as they are parallel to each other. You cannot do it to a force. Force should only be directed in one direction, whatever the direction it has. It cannot be translated. Okay. Okay, now let's talk about weight a little bit. So weight is weight is equal to mass times gravity acceleration. Weight is equal to mg. And I would like you to calculate like weight of your car or weight of your bicycle or whatever weight you want to calculate. And you just need the mass and you need the gravity acceleration. Multiply them and you calculate the weight, giving the correct number of significant figures. And the weight is the force. So therefore, weight is measured in newtons. Okay. The next slide is free body diagram. It shows all the forces applied to the body. Okay, let's look at the next slide, number 64. Can you see? The weight acts down, just like I told you before. My weight pushes on the chair, and chair pushes back with normal force. Yeah. And then force F acts to the right in my case, and friction force mu times N acts in opposite direction. So that would be free body diagram. We removed all the things around the body becomes free, but in order to keep things correct, we draw all the forces which act on the body. So that's called free body diagram. Let's look at the next slide, number 65. I show free body diagram. As you can see, mass is sitting on the surface, and we just don't see the forces yet, right? But if we remove the surface and we substitute the action of the surface on the body with the normal reaction and the weight of the mass as mg, then we get free body diagram for this case. And we will use the free body diagram when we solve the inclined plane problem. Slide number 66. So there is a sliding mass down the slope, down the inclined plane. Okay. So the forces are weight force, mg, force of weight, force of normal reaction, which will be equal to mg times cosine theta after we project all the forces on this axis perpendicular to the direction of the motion, and then we project all the forces on the direction of motion, and the weight mg will give us m times sine theta, and the friction force will be negative n times mu. Okay, and we write these equations. Let me show you how. Okay, this is slide number 67, right? So we add all forces as vectors, finding the resulting force. We project the forces on this direction, we call it x, direction along the slope, and we call the perpendicular direction towards n, we call it y direction. So here is x, and this is y, okay? So we do projection again on x and on y. We solve the equations using the second law of Newton. If the friction force is 0, then these are the solutions, right? Sine A times mg is equal to ma, slide number 68. M cancels out, so therefore acceleration is going to be equal to sine A times g. A is this angle theta. Can you see? This is A. I call this A, angle A. They call this angle theta, yeah? So that's for the case of no friction. This is the acceleration. Okay? Now, but if there is a friction, there are two kinds of friction. There is a static friction, which does not allow the body to move. But if there is enough force, the body starts moving, then we have mu, which is sliding friction, which is smaller than the static friction. And that's what I give you when we solve problem for the case of friction force. Use the free body diagram. In this case, friction force is active, slide number 70. As you can see, along x direction, there is mu times n. Is it? I think is it something wrong? Oh yeah, no, correct. All correct, yeah. Because mu times n is the friction force in negative direction. Can you see? This is mu times n, negative, correct? Yeah, and sine a times mg is this component of the gravity force along x, okay? Along y is n minus cosine a times mg, so this minus this, and because there is no motion in this direction, so n is equal to mg cosine theta, in my case cosine a, yeah? From here, n is equal to cosine a times mg. So substituting n into this equation gives us sine a mg minus mu cosine a mg is equal to ma. We cancel m, mass doesn't matter, so this is the answer for the acceleration. Sine a minus mu cosine a, the whole thing times gravity acceleration g, is going to be equal to the resulting acceleration. Okay? And I ask you to solve for your student number, given a, the angle, t degrees, in this case theta for them, for our case a, and the friction coefficient 1 over t. T is your student number, mod 100. Here is the YouTube video which explains this problem in more details. If you want, you can watch. I think it's about 10 minutes or 7 minutes. I don't remember exactly. And you have code which solves the problem and gives you the answers. Okay, any questions? So the next thing will be related to the center of gravity, because we'll be considering the block stacking problem. So slide number 72 tells you that the center of gravity is different from the center of mass, and the center of gravity is the center of parallel forces, which means that the torque is equal to 0 about the center of gravity. Okay. Next slide, 73. I ask you to solve the block stacking problem. It is kind of a puzzle, maybe for programmers, if you want to solve this kind of puzzle as a programmer, but using the laws of mechanics, we can solve it maybe even quicker than you do it on the computer. We try to find maximum hangover this distance, so that you can build like arcs, buildings, bridges, using blocks without anything, without concrete, without cement. People have been doing this for many centuries already. Yeah. The thing is that the hangover will be expressed through harmonic series, which is 1 over 2n. And it is diverging. In other words, if you have infinitely many blocks, you can have infinitely large hangover this distance. Yeah. So slide number 74 explains that. Yeah. We use the equations of static equilibrium to solve the problem. Hopefully, we can explain this in more details a little bit later, since today maybe we will not have time for that. And as I said, it's kind of a logistical problem which can be solved by computer programmers. Okay, so on the next slide, 76, I ask you to calculate hangover for S blocks, where S is your student number, which is approximately 22 million, right? And I'm sure your hangover will be only 16 meters, approximately 16 meters. Can you imagine? 22 million blocks will give you only 16 meters of hangover. And the code solves everything. And YouTube video also explains this in more details. If you want, you can watch, I think only 3 minutes this time. Okay, any questions? There is a lot. I'm sure you have many questions. Please ask questions. Are you with me? Hello? Hello?
Yes, sir.
Do you have any questions or comments? Okay, next slide, number 76, sorry, asks you to calculate the force, moment of force, I mean the force and moment of force. If you have moment of inertia, angular acceleration, and mass and linear acceleration. Make sure you give the correct number of significant figures and correct units. Any questions so far? Okay. The next slide is very important, probably one of the most important in mechanics. Excuse me. Sorry. So the spring force. Let me see if I can find it. Sorry, that's pendulum. Is there any waves? Oh, strange. Or maybe here, no? Oh, yeah. Can you see? Now, slide 81 shows you the spring and the mass attached to the spring, right? The spring has the property of K, and the K means that force is equal to negative K times X, where X is the displacement of the mass. And negative sign means that the spring will resist motion of the mass. Okay? Can be along X, like here, or can be along Y, like here. Doesn't really matter. We will usually consider Y because it is easier, but it doesn't really matter. So this problem is really important for many applications in physics. As you can see, like scales, like many devices based on these kinds of physical mechanisms. Okay. Similarly, pendulum is another thing which oscillates. Is it pendulum? No, this pendulum. Yeah. Thing, the mass on the rope on the cord, and it goes back and forth, oscillates, pendulum. Yeah. So that's why we are coming to the oscillation, which is periodic motion. We need to solve ordinary differential equation to describe oscillation. We can describe oscillation of mass attached to spring. This one. So these are the differential equations and the solution. I give you the solution, and K over M is the frequency, the angular frequency of oscillation, either for X here or for Y axis, doesn't matter, whether vertical Y or horizontal X. The equation is the same. Okay. So resonance is when the external force has the same frequency with natural frequency, in this case K over M squared. Then resonance means that amplitude will become almost infinite or very large, and that's probably the most important thing in telecommunication. Oh, okay, sorry. In telecommunication, in mobile phones, in internet and things like that. Hopefully we'll discuss that thing. Oh, I'm drawing, or someone is drawing, sorry. Hopefully we'll discuss it a little bit later, okay? So here is the period for the mass on a spring, this one, period of oscillation, 2 times pi times square root of m over k. K is the property of the spring and m is the mass. Pi is approximately 3.14, it's a number. So this is the period t, and I ask you to calculate this period. Make sure it's in seconds. Period is measured in seconds, yeah? And this one is for the pendulum. Same thing for the pendulum. The frequency, sorry, not frequency, period is L over G. L is the length, G is the gravity acceleration, pi is just a number, 3.14. And the frequency is going to be G over L square root. Remember, I showed you here. Can you see? G over L is the frequency. Square root G over L is the natural frequency of the pendulum, okay? But the period is 1 over frequency, therefore, it is going to be L over G square root, yeah? Okay, so I want you to find the displacement of harmonic oscillator, which is basically the sine, which is the solution for the oscillation. It's a sine function, maybe cosine. Doesn't really matter in this case, but we use sine. So this code solves the problem and gives you the numbers. Make sure you give the correct number of significant figures and the correct units. In this case, displacement is in meters. Okay. Next. Okay, here's the differential equation of the harmonic oscillator, okay? As you can see, we use y. Y2 primes means second derivative. T squared is from your student number. In this case, T is going to be natural frequency of the oscillation. And I ask you to use Wolfram calculator to solve this differential equation for your student number and to give the solution for y. Y will be measured in meters. Yeah, and T is going to be the natural frequency. Okay. Any questions at any point? Please do ask. I give you like a lot of stuff.
Sir,
Yes, question?
on slide 80.
80, just a moment.
Yeah.
80. Yeah, yes.
Why is vector key depicted with a jagged line? 80.
Oh,
And the
I
next
don't know.
slide.
I think I made a mistake. Maybe I drew something by mistake.
That's okay. Next
Okay,
slide.
any other questions? Okay, we'll discuss that one. Slide 87 shows the external force sine omega x. I use x instead of t because you have t capital here. To avoid confusion, I use x as time, doesn't matter. So it's going to be the differential equation. And I want you to find the resonant frequency when the resonance occurs. Obviously, if we divide everything by t capital, right, it will be y2 primes, L over t, so square root of L over t will be natural frequency is equal to 1 over t times sine omega x. So you will find a natural frequency using this code, okay? And finally, for the oscillation, this differential equation shows the resistance. So this m y prime, yeah, Chuck, just a moment. I think I made a mistake and that's why I drew by mistake. Yeah, I'm sorry. Hope it answers your question. Anyway, slide 88 shows you the resistance, the friction, this m which is your student number mod 35, times y prime gives you the resistance. So this is going to come to rest after some oscillation will come to rest, just like real oscillator, either pendulum or spring. It's going to be mathematically almost the same. And I ask you to use Wolfram calculator to solve this differential equation and to see if there is resonance or not. Questions about oscillations or anything else? Hello? That was a lot of stuff. I'm sure you have many questions. You know, I'm sorry that my name says Maria. Yeah, it's my wife's names. Yeah. In K to M, new messages, K to M. Oh, wait. Is it still slide number 80? Maybe here, just a moment. K to M. I don't understand. I'm sorry. Maybe here, no? Jagged line. Sorry, I don't know how to answer this question. I think I don't understand. Any other questions, please? Hello?
Sir, I have a question
Yes.
about the classical mechanics. Can classical mechanics be implemented in signal processing or data analytics to measure or predict change in physical condition, or the classical mechanic is limited for the implementation?
That's a really good question, and I need to think about that. It seems that classical mechanics gives you the understanding of what happens in computers, that kind of stuff, but I don't really know how to use it in information technology directly. I need to think about that. Okay.
Okay,
Yeah.
thank you, sir.
Thank you. So the last thing I would like us to talk about is the topic of waves. A wave is spread of oscillation in space. Okay, so oscillation happens at one point in space, whereas wave is the spread of oscillation in space. Okay, unlike material points, wave have the properties of interference and diffraction. Interference means many waves interact with each other, and diffraction means a wave is going around the obstacle, and it's not possible for particles. Excuse me. So let's look at another one. I ask you to solve the problem of guitar string oscillation. Maybe you like playing guitar, and there is a wave going through guitar string, and I would like you to calculate the displacement of the guitar string after s seconds and at m meters. M is your student number mod 35 and s is your student number. So it describes the motion of the string, and the code solves that complex problem, but in a very simple way. Yeah. And finally, the interference of two waves. As you can see, slide 91, there are two waves, first sine and second sine, sine omega t minus x over v. Here, x is the distance and v is the velocity. That's how wave moves, right? One sine and another sine using the law of sines will give you two sines times cosine, 2 sine times cosine. So basically, it's just simple mathematics, but in fact, it shows you that if the difference in paths is proportional to the wavelength, there will be interference. There will be like increase in adding maximas. There will be 2 instead of 1, right? But if it is halfway, it will be 0, so there will be nothing left. They will cancel each other out. So that's what I would like you to do. I would like you to give the interference equation for 2 waves using the code, which will give you the answer for the interference problem in this case. Okay, that's it for today. Any questions? I gave you a lot. I think I should go back maybe next week. Maybe we should go back and repeat these things maybe. Let me see. Oh, okay, just a moment. Let me see. Oh, this line. This means spring. I'm sorry. Yeah. Can you hear me? Hello?
Yes, sir.
This line means spring.
Sorry, my bad.
Spring. Something which resists pressure or stretch. If you stretch it, it will resist. If you press it, it will resist. It's spring. Okay, now I understand. Spring. Any other questions? Yeah, it is just a spring. I'm sorry that I wasn't clear enough. It's a spring. What is the Indonesian for spring? Let me see. Just a moment. Spring. No, sorry. Spring. Spring. Not this spring, sorry. Not the time of the, okay, let me show you spring.
I think you mean pegas, sir. In Indonesia, it's pegas.
Pegas, maybe just a moment. There we go. No, not this one. Spring coefficient. There we go. Can you see? This is the thing, yeah? Spring. Can you see that?
Yes, sir.
Hello? Okay, maybe this thing. Can you see this one? Do you understand now?
Yes, I understand. Thank you.
Thank you. I'm sorry for not being clear enough. Okay. Where is my... Okay. Finally, we need some mathematics. Maybe you can check out the angular calculus like degrees and radians, trigonometric calculus like sine, cosine, tangent, differential equations, functions of many variables. That's for later on. Vector calculus, tensor calculus, tensor. in our case is the moment of inertia tensor. Yeah. So maybe later on you will need those things. And you can use one of my websites if you want, or you can just use the textbook, or you can use the internet to understand the mathematics which we need in this class. Okay, let me see. Any questions about anything? Oh, sorry. Please ask questions if you have any questions. Any questions or comments or anything, please? It was a lot. It was a lot. English. Okay. Okay. Hello. We've been discussing so many complex questions today. Okay, so maybe we can let's see how many, 19 students. Maybe we can call it a day. What do you think? Hello? Okay, one new message. Yes. Yes, okay. So any questions or comments, please? Okay, so why don't we finish it for today? What do you think? Will that be okay?
Maybe before we end the class, I want to ask one question, sir.
Yeah.
Maybe I want to ask the main challenge in adapting classical mechanic concept in the technological application in this modern.
Yeah.
What are the main challenge in adapting classical mechanics concept to the modern technological application? What do you think
What is
about
the
that?
main challenge? I think the main challenge is that classical mechanics is like very basic science, but modern technological applications, maybe when you deal with, for example, when you deal with drone, for example, right? And you use, for example, artificial intelligence to control the drone, right? You need to use the solutions from classical mechanics to know how the drone will behave depending on your managerial influence. For example, you say on the engine or off the engine, or speed up or slow down or whatever. You need to know how the drone will react, and for that you obviously need classical mechanics. For example, right? If you use artificial intelligence, for example, to control something mechanical, you obviously need to take into account mechanical equations. I hope it answers your question a little bit. I need to think
Oh.
about that, you know. I don't know exactly the answer to your question. It's a really deep question, very interesting question. Thank you.
You're welcome, sir.
I will
Thank you
try
for
to
the
think.
answer.
Yeah, I will try to think. Maybe I can answer this better. Yeah. So classical mechanics is everywhere around us. So we cannot really avoid dealing with that. Every time you go by car or by motorbike or by train or by airplane, every time you deal with things like drones, like satellites, like telecommunication systems, you must deal with classical mechanics one way or another. Yeah. But I will think how to answer your question better. Okay, any other questions? Okay, then maybe we can finish for today. Thank you so much for your time and patience. And please let me know if you want to have like offline class or online class. What do you want? Do you want online class or offline class? What is better for you?
For me, offline class, sir.
Offline, right?
Yes, sir, offline.
Okay. Okay, great. So maybe we can take a vote. If majority of you wants offline class, I think we will do offline class.
For me, online is better, sir.
Okay, we have one. Yeah.
Yes, sir. I think online it's better.
Online, sir.
Okay.
Online is better, sir,
Okay.
because since I'm in North Sulawesi, so I can go to, yeah.
You know, maybe what I will try to do, maybe I will ask the university if I can have access to the internet from the classroom. So maybe we can try to combine somehow. I will think. Maybe we can do it online for those who want online, and hopefully maybe I can do it in the classroom so that those who can come to the classroom can have it offline. Maybe we'll see. But at this time, majority wants online. So I will try. You know, it's much harder to explain online because it's easier to draw on the whiteboard and it's easier to, you know, to interact with students than online. But online is good because you don't need to come to the university. It is hard to commute, you know. So we will think. I hope we will see. Maybe we can find a solution which makes everybody happy. Okay?
Okay, sir.
Okay, sir.
Thank you so much for your time and for your patience. Please enjoy your evening and have a great evening and take care and all the best. Okay?
Thank you, sir.
Thank you,
Okay,
sir.
thank you, sir,
you.
for
See you next
Thank
week,
you,
Thank
sir.
you.
Thank you so
Bye-bye.
much.
Thank you,
Good
thank you.
night.
Thank you, sir.
Thank you,
Good
sir.
night.
Bye.
Thank you. Bye-bye.
Thank you, sir. Good night.
thank you,
Thank
sir. Good
you.
night. See you next week.
Good night. See you.